talk about my favorite topic in mathematical physics, higher gauge theory. First, I need to say that in this talk, I try to avoid technical details as much as possible and focus on concepts and just introduce the concepts and maybe a little loose with definitions, but everything from mathematical point of view, everything is rigorous, and I try to give references it's needed. So the first part of my talk is gonna be about motivations and motivate you to study higher gauge theory, I hope. And firstly, I talk about Lie groupoids as a first example of higher geometry and generalized geometry. And I talk about a few out of many interesting things and tools that Lie groupoids bring to us. And next, I talk about the existing examples of higher gauge theory in physics, especially in theoretical physics and string theory. The second part of the talk, I introduce higher geometry. Then I just focus on the first example and easiest example that you can imagine for generalizing principal bundles, which are the foundations of usual gauge theory. And the last part of the talk, I introduce higher gauge theory. Firstly, I talk about fake flatness, which is the root of uh, skepticism against higher gauge theory, which is in the recent developments. There are, uh, people have get rid of this problem. Next, I try to give a formulation of a local theory which avoids fake flatness. And I don't talk about the global picture because it's more mathematically involved. And from the physics point of view, we only care about the local picture, which is a perturbation theory. Lastly, I talk about a very interesting example of this formulation applied to Lie algebroid gauge theories. So a Lie groupoid is first I want to introduce Lie groupoids. A Lie groupoid is nothing but a couple of smooth manifolds with a bunch of smooth maps between these spaces. You can also lift the notion of action of Lie groups to action of Lie groupoids on a manifold. Then a morphism between Lie groupoids by definition is bibundles, and you can also uh, have morphisms between morphisms, which are a two morphism, and it's straightforward to see, as you may expect, that this forms a bicategory. So, so here we are talking about the bicategory of Lie groupoids. The first interesting thing about Lie groupoids is the classifying space of Lie groups. So in classic geometry, it's the classifying space of a Lie group is a very complicated space. It's infinite dimensional and so on. If you allow for Lie groupoids and bibundles, you can prove in one sentence that the set of bibundles from your manifolds to this particular Lie groupoids defined out of your Lie group is the classifying space. In other words, the category of principal groups, principal G bundles on your manifold X, together with morphisms of principal bundles, is equivalent to bibundles from your manifolds to BG, which is also called the delooping. The next interesting thing about Lie groupoids is that you can think of them as resolving singular spaces. For example, if you have an action of a Lie group on a manifold X, you can form a Lie groupoid which has the same universal property that you expect for a quotient space. So you don't need the Lie group action to be a proper action to define quotient. The quotient always exists. In particular, when you're studying the usual gauge theory, we are interested in principal G bundles with connections and up to gauge transformations. Instead, this higher geometry would tell you to consider principal G bundles with connections as objects of your Lie groupoid and gauge transformations as morphisms. So it's another way of thinking about the quotient. And it's very interesting that you can differentiate Lie groupoids, which give you a DG manifold or a Lie algebroid, and it's the same as the BRST formulation of your gauge theory. So in this sense, higher geometry integrates perturbative field theory. And another example are orbifolds, which are studied and they're a special kind of Lie groupoids. You can think of them as a special kind of Lie groupoids. Now, I will tell you that how Lie groupoids are the first example of higher geometry. But before that, I want to talk about the existent examples of higher gauge theory in physics. In physics, we are only interested in, we only know the perturbative stuff. So we are only interested in infinitesimal version of higher geometry, which are Lie algebras or more generally Lie algebroids. The definition is given, but we don't really need the full definition to talk about it. But the first appearance of an infinity algebra in physics was in closed string field theory, when Zuybach showed that you can write a string amplitudes in terms of some functions satisfying some identities. And those functions and identities just define an L-infinity algebra. The next example would be Young-Mills supergravities and especially the B field. In a standard model, we know that if you have a particle, the particle can couples to a one form through its word line. So similarly, a closed string can couple to a two form, which is the famous B field, to its word sheet. And it is shown that this is essential to see this two form as a connection on U1 which is just a special principal two bundle. So it's a connection on a higher principal bundle. But more specifically in Young-Mills supergravities, it's much more essential to think in the higher geometry point of view because the one form potential mixed up with the two form B field through the three form curvature, which is given here. And so there is an Lie2 algebra underlying this theory. And this Lie2 algebra is called in special cases, the string Lie2 algebra, which can also be lived to Lie2 group, which is called the string Lie2 group. And this Lie group is very important in physics. It's an analog of a spin group for a string theory. The next example is M theory, or in particular, the interacting M5 theory. So it is postulated by Witten many years ago that there should be a theory which is called the 2, 0 theory, describing interacting M5 branes. But later on, Witten himself, along with many others, argued against the existence of this theory at Lagrangian level. So they believe that 2, 0 is purely quantum mechanics. And the heart of this belief is that we didn't have a formulation of higher gauge theory, because we already know that M5 branes should be higher gauge theory. Uh, the, the reason is that if you the reason is that M2 branes end at M5 branes. So the edge of M2 branes is a line which moves around in your M5 brane, and it's a higher dimensional object. So it should be described by higher gauge theory. And recently, there was a development of higher gauge theory and how you should define it. And in particular, there is a candidate for describing M5 branes uh, that it has passed uh, many arguments, like you can uh, you can get the string theory out of it, but it's not conclusive. Now, with these motivations, I want to move on to higher geometry. So first, I want to introduce a higher category theory, which is the underlying of higher geometry. The interesting question that I want you to think about is the following. So if you have a topological space, let's say X, you can consider the path groupoid, which is the category. The path groupoid consists of points of your topological space uh, as objects, and paths between these points as morphisms. But we all know that we have to consider these paths up to homotopy. This is how it works, right? And but this is not the most natural thing to do. The more natural thing is that it's obvious that homotopies between paths are themselves a higher dimensional path. So a homotopy is a path between two paths, right? So it's a morphism between morphism. This is the idea of higher morphisms. And people with this particular example in mind, people have defined infinity categories. So the resulting infinity category not only resolve the homotopy category that you wanted to think about, but it also has a lot more information. The definition, the final definition is the following, that an infinity one category that we are in this talk, we are interested in infinity one category. An infinity one category is a category enriched over infinity groupoids. First thing that we have a notion of infinity groupoids. I will introduce them. So roughly speaking, between two objects in your category, instead of having the set of morphisms, you have a groupoid. you have an infinity groupoid. So the idea is that you replace sets with infinity groupoids. So, but the detail of what is an infinity groupoid is not very important. There are many models for infinity groupoids which are all equivalent, and all of them are very successful in mathematics, especially algebraic geometry, algebraic topology, and homotopy theory. But the I want to introduce, I want to invite you to think about replacing sets with infinity groupoids. Now, with this in
Sorry,
mind,
can you please explain the name? So why is it called the infinity groupoid? And what's the idea, roughly?
yes, so the idea is that the, of course, there is a historical reason, but the idea is that here, if you think about homotopies between two paths, you're talking about a morphism between morphism, and it goes like up to infinity. Then you have, if you call them two morphisms, then you have a homotopy between homotopies, which is the trimorphism. So you have a tower of different kind of notions.
So it's like recursive.
But another reason is that before knowing the notion of infinity categories, we already know the notion of a two category. This people knew this before introducing infinity categories. And you can see that infinity categories are generalization of two categories.
Why infinity comma one?
The one means that every n morphisms such that n is greater than one, the morphisms are invertible. It's a technical point that because of this one, we are introducing infinity groupoids. So it says that any n morphism such that n is greater than one, that morphisms must be invertible.
Okay, thanks. So you could define infinity two and so on.
Yes.
But the n equals 1 morphisms are just the paths between 2 points, right? So why aren't they invertible? If you just
Yeah,
path
in
backwards,
that in that case, the path groupoid that I introduced happens to be infinity zero category, any morphism in invertible. But this is a special feature of the first category. It's not a generic feature that we are interested in. The generic feature is that if you have a homotopy category, you can resolve the homotopy category to an infinity one category. You can always do that. But not all morphism in your homotopy category is invertible. In path groupoids, yes, the morphisms are invertible. So I want to generalize the notion of sheaf. We know that for any category C, a sheaf is a contravariant functor from your category to the category of sets, right? With some axioms that we don't care at the moment. So an infinity sheaf is just replacing sets with infinity groupoids. Now, the notion of higher geometry comes into the picture. So this is the definition. But I want to forget about the abstract definitions, and I want to focus on a very easy example, which is a strict principal two bundle. For it, a general theory of infinity bundles is developed by Urs, especially by Urs, and but we don't want to talk about the general concept, which is a lot mathematically involved. Let me focus on a strict principal two bundle. First, I need to generalize the notion of Lie group to a Lie two group, and a strict one, of course. So a strict Lie2 group is a Lie groupoid. So the underlying set theory of Lie group is generalized to Lie groupoid. So the sets are replaced with Lie groupoids. So a strict Lie2 group is a Lie groupoid together with a composition functor, inverse functor, and identity functor. And they obviously satisfy the evident conditions that you imagine for Lie groups. And of course, you can also leave the notion of action. For making things a lot more concrete, there is a theorem saying that a strict Lie2 group is the same concept as cross modules of Lie groups. So a strict Lie2 group consists of two Lie groups, say G and H, with a group homomorphism and an action of Lie group G on H by automorphism, satisfying these relations. Now we have everything to define principal two bundles. So a strict principal two bundle again is a Lie groupoid together with a surjective submersion to a manifold M. I want to focus on the example that the space-time manifold that you want to construct your theory is just a manifold. It's the simplest thing that you want to imagine. So a strict principal two bundle over a manifold is a Lie groupoid with a surjection submersion to M, which is respected by your right action. It's just a lift of the definition for principal bundles, right? And a morphism of principal bundle is an equivariant bibundle. So this is the abstract notion of bundles. So in the same way that the classifying space of a Lie group is described by a Lie groupoid, the classifying space of your Lie2 groupoid, so your Lie2 group is a Lie2 groupoid, but at the moment we don't want to introduce them, just so you know. And there is a powerful theorem which make you able to describe principal bundles more easily. It's the co-cycle picture. So you can see that any strict principal two bundle is described by an open cover and a bunch of maps, which are called the co-cycles. And so for any pair of open sets, you have a map Gij to Lie group G and Hij on an intersection of three open sets to H, satisfying the generalized co-cycle relations. And this is a non-abelian cohomology which people have studied. It's a zero non-abelian cohomology. So any strict principal bundle is a strict principal two bundle is classified by this information. So now that we know higher principal bundles, we want to talk about higher gauge theory.
Wait, so can I ask a question about, can you go back one slide?
Sure.
So in this old picture of just thinking of the simplest abelian two-gerb in terms of something where over triple intersections you put some kind of phase.
Yes.
So can I think of this G as being the gauge group there, the fiber of something which isn't quite a bundle because you have some three class, and then these triple intersection going to H is being kind of this Dix-Meredwadi.
The classical U1 germ, you want
Yeah, the classical U1 gerb. So there would H be U1. I mean, how does this example work for the
so
classical U1 gerb?
that example is by considering G to be trivial and H to be U1.
Okay. And so would this just be the Chekhov homology construction then of the Dix-Meredwadi class, where you have something on each of those
Yes.
triple intersections?
Yes. The first thing that you need to know about higher geometry is that although principal infinity bundles are well defined and everyone is happy about the definitions, the notion of connection on higher principal bundles is not settled yet. There is a lot of problems. There are many different definitions and which are not equivalent, and many of them suffer from fake flatness, uh, which is the heart of skepticism against higher geometry. But we want to address these problems. The notion of fake flatness is very important to us. So the first example of fake flatness is that when you want to consider a two-gauge theory, a two-gauge theory is locally described by a one-form potential and a two-form potential. And the fake flatness says that your one-form potential, the, the the curvature assigned to one-form potential is zero. So the one-form curvature is flat. This is a very horrible condition. First of all, you cannot think of a gauge theory trivially as a two-gauge theory because it only describes flat connections. So fundamentally, there is something wrong with this condition. The next thing is that these conditions make your theory very bad and very non-interesting because you can gauge away the one form, at least locally, and it becomes useless in physics. Many examples that we have in physics, they don't have fake flatness condition. So we want to get rid of this problem. To give at least a local theory, I want to introduce the notion of graded manifold. So a graded manifold, it's a very technical definition that I don't want to get into detail. So a graded manifold is a locally ring space. So you have to think about graded manifolds in this way, that a graded manifold is a topological space together with a notion of functions. They're not really functions. You have to think about them in that kind of there are functions, but you have to define it for your graded manifold. An important example of graded manifold is the shifted tangent bundle. So the definition of shifted tangent bundle, T1M, is that your topological space is the topological space of M, and the algebra of functions are defined to be the algebra of forms. So moreover, a differential graded manifold is just a graded manifold with the notion of differential on your algebra of functions. So in the example of shifted tangent bundle, the differential is the de Rham differential. Okay, so this is the definition of DG manifolds or differential graded manifolds. So locally, if you have any L-infinity algebra, a local connection on a manifold X, which should be seen as your space-time, is just a map of graded manifolds from your shifted tangent bundle to your L-infinity algebra. There is a theorem saying that there is a bijection between maps. There is a bijection between maps to your L-infinity algebra, which are just a map of graded manifolds, to mapping of differential graded manifold to the tangents of your L-infinity algebra. So in particular, so what I mean is that the set of map of grading manifolds to G is the same as map of differential graded manifolds to T1G. I didn't define a T1 on a general space, but it is defined, and we don't really care about the deep detail of definition. But but we want to also talk about gauge transformations. Gauge transformations are going to be defined using similar constructions to AKZ. Probably AKZ is familiar to the physicist. Okay, let me give the abstract definition. Given an L-infinity algebra, first of all, there is a definition. There is a theorem saying that L-infinity algebras, or more precisely, L-infinity algebroids, are the same as DG manifolds. It's the same notion. So given an L-infinity algebra, you can think about, you can define the flat BRST. So the flat BRST is going to be your describe your perturbative field theory that you want to describe. So this is first of all the flat case. I will lift this definition to the full BRST. So the flat BRST is the representation of this preshift that from NQ manifolds to the category of sets. First of all, the NQ manifolds are just differential graded manifolds, just with non-negative degrees. So if you put differential graded manifolds here, you get the BV. But we are not interested in BV at the moment. We only care about the non-negative part of the theory, which are gauge fields and gauge transformations. So we restrict this to the NQ manifolds. The preshift that we are interested in send an NQ manifold to the set of maps, DG maps, from chi times your T1M to your L-infinity algebra. First of all, the reason that this is a flat case is that you're talking about DG maps to L-infinity algebras. And because it respects the differential, it's flat. But okay, so in the case of G being just a Lie algebra, you immediately see that this is exactly the BRST of flat connections that you know in gauge theory. The case of Lie-2 algebras are also calculated by Simon and Schmidt in 2020. Now, as I said, there is a natural bijection between graded maps to G and differential graded maps to T1G. So the first step to lift the flat connections to non-flat connections is replacing G with T1G. But making this space bigger, you get more connections, but you also get more gauge transformations. So to restrict that, the first thing is that you need a notion of curvature. You have to differentiate between connections. What is the connection? What is the curvature? So to do that, you have to define a decomposition of T1G to your G and some other space which serves as curvature. And you can show that if G is an L infinite, so you can show that if G is a Lie algebra, this is unique. So, but in general case, this is not unique, and it's called adjustment datum in the literature. This is a missing point of other. This is the missing point in some literatures, that they cannot define a proper connection, because if you choose a wrong adjustment datum, you get a bad theory. So you need to have a good decomposition. The full abstract definition is the following. So if you, for a given NQ manifold chi, you send this to the set of maps F, set of DG maps F from chi times T1M to T1G, such that it satisfies this commutative diagram. In this commutative diagram, the absolute of chi is just the underlying manifold of chi. So the F bar is going to be your curvatures. So this condition says that this restrict the curvatures to define on just the manifold chi. So the abstract definition is that the full BRST is the representation of the pre-shift that we described. Okay, this is the abstract definition. But how do you construct the representation? The representation is usually constructed using the same methods as in AKSZ. So the BRST manifold, the degree zeros are going to be connections, and the higher degrees, the degrees 1 elements are gauge transformations, degree 2 elements are gauge of gauge, and so on. So you have a constraint on your on your maps F. So how do you translate and describe this condition? So in the AKSZ construction, you construct BRST, the degree zeros of BRST as maps from T1M to T1G. To construct higher degrees, you consider all maps that have different degrees. So you usually think about mapping of manifolds such that they respect the grading. So to construct the BRST, you have to think about general maps that do not respect the grading. But the condition says that if you map to the curvatures, the curvatures should always be degree zero. So there is no gauge transformations assigned to curvatures. So in other words, we are looking for connections and flat transformations. So again, I want to emphasize that this diagram condition says that the curvatures are degree zero. So the curvatures do not have gauge transformation. They transform under gauge transformations, but there is no gauge transformations assigned to curvatures.
So has this been applied to that example you gave before of gauge supergravities? So is this
Yes,
degree zero condition something familiar there?
yes.
So
So
what is that degree zero condition then in the case of the gauge supergravity example that you gave us?
here, the H is defined in terms of B and A. So you have to deform this definition of A, this definition of H, with some elements which involve F, the two-form curvature, right? And because the gauge, the condition that I told you about depends on the notion of curvature, this changed the notion of gauge transformation because it changes the notion of curvature. So this particular example is studied in this paper, and the full BRST is calculated.
Okay, so that deformation of H is something like H minus DF.
Yes, something.
Okay.
Or the deformation contains A and F. It can be DF or AF, something.
Because you want a closed form maybe, so and H
These
is
two are
gauge constrained, but
equivalent,
it's not
right?
a closed
AF
form.
or TF, because F satisfies the Bianchi identity, so whether it's DF or AF, they are proportional to each other, no?
Yes, maybe. Yeah, I don't know the answer. I don't want to say something wrong. But in the case of gauge supergravities, has an underlying Lie-2 algebra, which is the string Lie-2 algebra. And this particular example is considered in this paper. So again, the full BRST is constructed by considering maps of different degrees, maps that do not respect the grading, such that the corresponding curvatures are degree zero. If you don't choose a good decomposition, you get fake flatness, and I will give you a concrete example. So in the case that G is a Lie algebra, you can immediately see that T1G, there is a unique decomposition. The reason is just a grading reason, because T1G is represented by one form, a degree one element, which is the connection, and a degree two element, which is a curvature. And there's no way that you can mix them. There's a unique decomposition, which is given by grading. But if G has if G is bigger, you can mix them. Like you can mix H and F, right? You can write deform H by AF or DF, but here there is no way you can deform curvature. And fake flatness condition arise when you don't consider a good decomposition, and also the BRST for the string to lead to algebra is considered in this paper, which is a very important example because it's also used to define a gauge theory, which is a candidate for M5 theory. So now I want to apply these definitions to Lie algebroids. So the Lie algebroid example is important because you don't need a string theory and abstract according to mathematicians, abstract nonsense stuff to talk about higher gauge theory. You can talk about a standard model. A standard model is a gauge sigma model, and the underlying is a Lie algebroid. So the infinitesimal of a standard model, which is an infinitesimal or perturbative theory, is constructed by putting G to be a Lie algebroid. In the standard model, it's a little trivial algebroid, but generally can be more complicated. Fix a Lie algebroid G with the underlying manifold X. If you have a Lie algebroid connection, nabla, it introduces a decomposition of T1G. This is proved by Arias, Abad, and Kranik. You can pick this decomposition and construct your theory. The degree zero elements of your BRST is the connections, as you imagine. So a connection is given by a pair, phi and A, where phi is a map from your space-time, the underlying manifold of your Lie algebroid. So in the case of a standard model, X is Rn, but generally it's a very smooth manifold, and A is a phi star G valued differential form. So it's a Lie algebroid valued differential form. The one form curvature is defined, is given by d phi minus rho of A. Rho here is the anchor map of your Lie algebroid. In a local coordinate, the two-form curvature is a little more subtle to see, but in a local coordinate, if you choose a local coordinate for your Lie algebroid, you can write down your two-form curvature. And here, omega is the coefficients of your connection nabla. The infinitesimal gauge transformations are given by a Lie algebroid valued function. The Lie algebroid valued function C, and the gauge transformations are given by these two equations. You can, if you just forget about how you arrive at these definitions, you can just think about someone is given you these equations, and you check that the gauge transformations close if pi is 0 or nabla is Cartan. So if you don't choose a good decomposition, which is given by nabla, you get a fake flatness condition, which is pi being 0. So the one-form curvature should be 0. So in this case, a good decomposition is nabla being Cartan. If nabla is Cartan, you get a good decomposition. This particular example is not published yet. It's going to be published in 1 week or so, we hope. So that's everything that I wanted to talk about.
Okay, thank you. That was very good.
Can I ask a very naive question here?
Go on.
I was wondering, where does RG flow fit into your theory? Like how the change of a scale fits into your theory?
In the Lie algebra, it does not.
I see.
The theory that from a math, for me, a perturbative field theory is nothing but BV,
Mhm.
and you cannot talk about RG flows in BV. It's not a perturbative concept, right? Like
Okay, thanks. I'll think about it.
Another naive question, maybe. So, can you define what you call fake flatness?
Yes. There's no like a concrete definition, but if you think about the examples, that for example in this example, if you don't choose nabla to be Cartan, the gauge transformations do not close. You get a condition such that the gauge transformation closes. So in this case is the one-form curvature being 0. For the case of gauge supergravities, in this case, the condition is that the two-form curvature F has to be 0. So let me be a little more precise. So if you take this H and you do not deform H at all, you get fake flatness. The fake flatness condition is that the two-form curvature F has to vanish. But if you a little change your definition of curvature, you can deform H using F by term DF or AF. Then the resulting gauge transformations close with no condition.
Just for this example, you are assuming that A and B are in the same algebra. They are both in the same representation of some group, or
in the tensor hierarchies conditions, in the tensor hierarchies that people consider gauge supergravities, there is conditions that comes from physics point of view that they should satisfy some representation conditions. Yes, in that sense, yes. People in physics used to consider this stuff, and yeah, I believe it's called tensor hierarchies conditions.
yes, but just as a simplest possible example that you could make. So you're assuming that, for example, A is in some algebra, and then B should also be in the same algebra, so it transforms covariantly under the transformations of the standard gauge transformations of A and so on.
I don't really wanted to talk about the supergravity. So if you don't consider the supergravity point of view, and you just want to talk about the one-form potential and a two-form potential coupled together.
Yes, that's what I mean.
So in that sense, there is no condition, there is no representation conditions. You can just consider these curvatures and so on, because we don't want to talk about physics. But when you go to the physics point of view, people, of course, have more conditions. And
even in
yeah, I
physics,
understand that there
maybe
can be
there's-
concrete. Mhm.
well, even in physics, I mean, I don't think A and B have to be the same algebras, no? I mean, they're kind of measuring different things. So A should be whatever the gauge group is, and B is maybe counting M5 branes or something, or it
yeah,
depends on your.
yeah, H and B are take values in the same algebra.
I
H
mean,
and B.
yeah, I
Oh, I thought you
understand
said
that.
A and B. Oh, H and B. Yeah, H and B are the same.
Yeah, I was asking about A and B actually, and I
Oh,
mean,
so
in a sense, in this setup, I
so
mean, concrete models can have different things, but I mean, like, what is the general property that you can have? So, for example,
yeah,
here I see that the Chern-Simons term, it seems that these brackets mean that you take trace. So it's just like singlet, B is singlet of the gauge group.
I
yes,
think you had a slide on this, no? Where you showed the quadruplets, G, H with a triangle operator, and the other one, which had kind of the relation between these two things. Earlier, near the beginning of the talk, you showed that you could show you had these
no,
with a quadruplet G, H, delta. You had like a homomorphism from H to B, and you also had a group action of G on H.
oh, you mean
That
this?
was your kind of general structure. Yeah, this
Yeah,
one.
yeah.
Yeah.
So in this particular example of gauge supergravities, H is U1, right? Because it's just a B field, and A takes values in a general Lie algebra. So G is a general Lie group. G is a Lie group of your gauge theory, and H is U1, right? And you need to have these maps, other maps. If you want to lift gauge supergravities to a non-perturbative picture, in the perturbative picture, of course, you need the linearized maps. We only care about the linearized picture of this.
Okay, but if we don't talk about the standard supergravity, we want to do something that is higher gauge theory, right? Then
Yes.
two forms should take volume in some non-trivial.
Yeah, if you have multiple
representation.
M5 branes, for example, then the H, I guess, would be something non-abelian, maybe more complicated, counting the number of with a rank equal to the number of M5 branes or something.
Yep,
Yeah, so that kind of example, I want to understand how it works and what is the fake flatness and how does it change? How do you get it rid of?
yeah. So that example. Let me see if I have the morphism, the reference here. Yes. So yes. So the M5 theory, people have considered this theory in this sense. So I believe that the H is it's the underlying theory of M5 theory is the string 2 group. The string 2 group is a very a little complicated group that is people have considered. So but the underlying, so the string 2 group so the string 2 group H and G are complicated, but if you go to the linearized picture, it's way more simpler. The linearized picture is given so the linearized picture is given by a Lie algebra. You can take, for example, SUN or something. But the H, the linearized version of H is just R. Is a so you can think of H as U1, and the L infinity. So that you have to define the L infinity structure on them. So the L infinity structure is defined using a higher co-cycle of Lie algebras, right? So you see that these elements, the Chern-Simons term, in the Lie, if you don't think about the connections, if you just think about the form, it's just a tree co-cycle, right? It's the H3 of your Lie algebra to U1 to R, the linearized of U1, right? This is a tree co-cycle. This is the string Lie2 algebra.
I'm not sure I fully understand. I will have to probably look up the paper that you mentioned.
So what's this obstruction to the renormalization group with BV? I mean, people like to do anomaly matching, and I thought the first paper there was Zumino's paper where he was looking at the grade 2 in BV to see that that was matching the anomaly conditions at different energy scales. And that's where it came from, but I don't know. I haven't really been following the story. So, I mean, I thought with BV, you're supposed to get some sort of isomorphism of cohomologies for every,
Yes,
like whenever you have a dual description valid at different energy scales, at least. I don't know about local renormalization group flow.
I don't know all the literature. Maybe there is probably there is something that you're mentioning, but in my knowledge, I see BV as a differential graded manifold, and the algebra of functions assigned to this differential graded manifold is the algebra of observables. Algebra of local observables, right? For
Yeah.
example, action is an observable. The BV is only interesting. So two BVs are the same if they have the same cohomology, or in other words, they have the same S metrics.
Right. So that was the claim I thought that renormalization group flow induces an isomorphism on the cohomology.
That can be interesting, yeah, but I don't know the detail. Yeah.
Okay. Okay. So any more questions?
Yeah, I think I have a kind of a crazy question. What you talk about seems to be closely related to the high form symmetry, like p-form symmetry. My question is like there, the symmetry is really global. Is there any way like you can gauge that, get a higher gauge theory from there?
Yeah. Yeah, the two branch of higher form symmetries and higher gauge theory are kind of separated. High,
Mhm.
the higher form symmetries that people usually consider, they talk about global symmetries, and
Yes.
they talk in some examples they talk about also gauging the higher form symmetry, but they have a different notion of gauging. They
I
they
see.
they usually use okay. So okay, I know this particular thing that if your higher form symmetry is discrete, is a finite group, the gauging procedure that they consider is kind of they call it a Fourier transform. I don't
Oh, I
really
see.
know what it can mean, but
They go to momentum space or something and call that gauging it
no, no, I don't
for
think
transformation.
no, I don't think so. So the thing is that they consider elements like they they add Wilson lines, kind of
Yeah,
similar thing to Wilson lines to a path integral. So because Wilson
yeah,
line is e to the I g,
yeah,
it
yeah,
kind
exactly.
of similar to this construction. That's why they call it Fourier transform. but
Oh, I see.
but
Okay.
it's a completely different thing. So the underlying category theory is the same. For example,
Mhm.
the higher form symmetries form a higher group. It forms a two group. For example, if you consider zero form symmetries and a one form symmetry, they form a two group. So they usually form they form a two group, and usually they only consider the cases that H is abelian.
Abelian
Because
case. Okay.
they have this picture that you can move around one form objects
Mm.
in your path integral. So H must be abelian.
Yeah, so no Lincoln number there, right?
Yeah, problem. Yeah.
Yeah, there's no linking
Oh,
number. That's the argument. You can't have any linking number because the total dimension is less than the total dimension of the two objects is less than the dimension of the space, -1. So that's
yeah, I
why they can
see.
prove that every higher form gauge symmetry is abelian.
Is it
But
oh
there
yeah,
they're
yeah, now.
gauging at the level of state. Here it seems like
Mm.
you're doing something else. Well, I mean, I guess the degree 0 BV should somehow be related to the states, but you're looking more at
Mhm.
the algebra. I don't know how much you're looking at the
Yeah.
space of states. So if
Mm.
you would see, I mean, maybe you're looking at different objects. It seems kind of strange there should be two different notions of gauging, but maybe this
Yeah,
gauging in the sense of the higher form gauge symmetries, you're not exploring what it should do to the quantum states or to the Hilbert space. I mean, you haven't mentioned the Hilbert space.
I don't want to say something wrong, but they also have this picture of topological field theories that, a quantum field theory is a boundary of a topological field theory in a higher dimension, and a
yeah,
gauging changing the boundary condition somehow. They also have some definitions like this.
I see. There's a lot to think about. Thank you.
Thanks.
Thank you. It was very nice.
Thanks. I hope you get motivated to study higher gauge theory, and at least you enjoyed the talk.